Okay, so let's first state what is actually Lagrange's theorem. So theorem. So let G be a finite group and H be a subgroup of G. Okay, then order of H or the size of H divides order of G. Okay, this is what we have to prove. So for example, like I should take, for example, you have seen H is a subgroup, right? Of what? Of Z9. And in this case, what is order of H? What is the size of H? Which is 9, which is 3, right? And order of Z9 is 9 only. It is very clear that order of H divides order of G, because 3 divides 9. So you take any subgroup of a finite group, then that size going to divide the size of the whole group. That is the idea. So we need to so let's look at how can we do this, right? So first thing we have to we want to define a relation. Okay, so what is the first claim is let H is a subgroup of G, where G is finite. When define a relation for all A and B, for all A, B in G, define a relation A, the relation I denoted by this tilde H. So it is if and only if A is equal to BH for some H in H. Okay, for some H in H. So this is a relation. So if A related to B, if A can be written as BH for some H belongs to H. If you are able to write in that fashion, yeah. So what is my claim is this tilde H is an equivalence relation. Equivalence relation. Okay. So first what I have to prove is it is reflexive. So first thing is tilde is reflexive. So why it is reflexive? Because every A can be written as A times E, because the property of identity. Now E is an element of H, because H is a subgroup of G. So you got A is equal to A into E, where E, so that means A is equal to AH, where H belongs to H. So that H is E, that is A related to A itself. Okay, so it is reflexive. For every A it is true. Okay, for every A this is true. Now symmetric. Symmetric means you have A related to B, that means A is equal to BH for H belongs to H. Now you know that if you multiply, because H is in H, H inverse is in H, right? Then what happens? You multiply right side by H inverse. So what you will get is B, or what you can write it is B is equal to A H inverse. This H inverse is an element of H, so it is of the form some B is equal to AH. That is, B is H dash H. You don't directly write it, because you don't have to improvise it anyway. You understood? B is equal to A into some element which is in H. That means B related to A. So A related to B implies B related to A. Third one is transitivity. So transitivity means A related to B is given, similarly B related to C is given. That is A is equal to BH for some H in H, also B is equal to CK for some K is in H. So from this what we can write is A is equal to CK times H. So that is equal to KH. Now K and H are elements of a subgroup. That means C is equal to some M, where M belongs to H. So what you got, that A related to C. So this is an equivalence relation. So why it is important to prove it is an equivalence relation means, um, so there is equivalence clauses of this relation. So what are the equivalence clauses? So let's take an element in G. So what is the equivalence clause of A? So what do you mean by that? All elements B such that A related to B, right? Or we can write B such that B is equal to some A times H, where H is in H. So this can be written as simply AH, where H belongs to H. What is this? AH. So it is a left coset. So it is a left coset of H in G containing A. Now it is not simply relation, it contains A. Why it is contain A? Because if you put H is equal to E, A times E belongs to AH. So now the coset contains the element A itself, but it is in general it need not happen, right? Only if E is available inside, then only we can make this happen. So now this, for every coset of a subgroup H, AH is a coset containing H. So this coset is an equivalence clause. So what is the idea is, you know that an equivalence relation, an equivalence relation gives rise to a partition using equivalence clauses. So what is the idea is, you can write your entire group into union of cosets, where A belongs to A distinct, A is the distinct representative from a coset. Why I am telling it is distinct representative? Because in the example Z9 you have seen that 0 plus H is equal to 3 plus H equal to 6 plus H. So in all these cases they all cosets are equal. So you don't have to select all the elements, all the 0, 3 and 6. You choose only 0. Okay, so what we have seen before that, it is 1 plus H is equal to, I will write it again because it is 7 plus H. So 2 plus H equal to 5 plus H equal to 8 plus H. So what is distinct representative means? 0, 1, 2 is a distinct representative, 0, 3, 4, 5 is a distinct representative, 6, 7, 8 is a distinct representative. So you can see this is in fact true, because if you take Z9, find the union of this. What is 0 plus H union 1 plus H union 2 plus H? So if you can see 0 plus H was exactly 0, 3, 6 union, 1 plus H was 1, 4, 7 and union 2 plus h was 258. So they are all mutually disjoint. Also their union is exactly Z9. So that's what we can say. So equivalence classes gives rise to that. So moreover, you can see G, the cardinality of G is equal to, because if you use principle of inclusion exclusion, what is the union of this? Union of AH. So this is equal to summation cardinality of AH, where A is distinct representative of cosets. So I will call it dr cosets. Okay. So this is true, right? This is true. In here also you can see it is true, because Z9 can be written as 3 plus 3 plus 3, which is 9. Okay. So this is let's keep this in our mind. Now another claim what we want to prove is, we prove that for any, if H is a subgroup of G, then for any A in G, we will prove that the cardinality, the size of AH is exactly equal to the size of H. So how do we prove this claim? So this is done by bijection. So we know that if you are able to, so we recall the remark. So let A be our finite sets. Finite sets. If there is a function A to B is bijection, that is 1 1 and on 2, then their cardinalities are same. Okay, because you can pair it. So that means the A has same number, B has the same number. In that light, what I want to establish, I want to define a function G from H to AH, and I'll show that G is a bijection. So how do you, so what is that function? So it is very easy one only. You take an element in H and map it to AH. So I will call, how do you prove this is injection? So 1 to 1. So this is 1 to 1 because, so what is here is f of, or G of H is simply A into H, because AH is belongs to H only, right? So what do you want to prove 1 to 1? So take G of H is equal to G of K. Then what do you have? AH equal to AK. Now multiply both sides by A inverse, because it is a group. So what do you get is EH equal to EK. This implies H equal to K. So f of x equal to f of y implies x equal to y. So it's 1 to 1. Now how do you prove it is onto? Onto means you take an element from AH. Okay, right? Then my claim is A inverse y will map to y. So claim is very simple. I prove that A inverse f inverse of y is equal to y. And first thing we have to show that A inverse y belongs to H. So how? So y is in AH means y is equal to A times some small h, right? Then if you act on A inverse of y, what happens is A inverse of A H, this will be EH equal to H. So that belongs, this is an element of the domain. So A inverse y is in fact in H. So this is true. Now whether this maps to a y. So let's see what is A inverse y happens. So f of A inverse y is what? A of A inverse y. So that equal to EY is equal to y. So So for any y, so what we have proved is for any y in AH, there is a x, in fact who is that fellow, A inverse y in H, such that f of x equal to y. So that is the idea of onto, because every element in the codomain is in the range of the function. So what we have just proved is the cardinality of H is equal to AH. What is it? Why it is useful? Because you have already written G is equal to the sum of A is a distinct representative from Cosets, right? And this is equal to AH. So now this cardinality is depends on A, but you can change it to cardinality of H only, which is independent of A. A is a distinct representative cosets. Okay. So now this will look at something like this. I'll call what is it is, right, because H, now H is independent of anything. You are adding, this is how many, this is the number of distinct cosets, okay. So whatever, so that is a number, right? So cardinality of G is equal to GH multiplied by H, and this is a number. We also call this is index of H in G. So the meaning is number of distinct cosets, the number of distinct equivalence classes. So you know that this is a number. If this is a number, then what you can say, cardinality of G is equal to some number H, or you can give some number like some K into H, where K is an element of integers. In fact, it is a number of elements, so it's a positive integer. That means the cardinality of H divides cardinality of G, or similarly you can write order of H divides order of G. So you can see this number is in our example, this number is turned out to be, if you take G is equal to Z9 and H is equal to 036, this number index of H in G, similarly we can write Z9 with that subgroup H is equal to how many distinct cosets were there? There was 3 distinct cosets, right? So this number was 3. So Z9 can be, it was written as 3 times 3. So this was your index. Okay. So this is idea. Okay. Now think about the other version. If what we have proved is, if H is a subgroup of H, this implies order of H divides order of G. But if any number divides, so suppose K is a divisor of order of G, does there exist a subgroup H of G where order of H is equal to K? So this is the converse of that statement. Okay, check whether it is true. Check. So this is true, that is called Lagrange's theorem. Now my question is, if K is a divisor of order of G, does there exist a group such that order of H is equal to K? Okay, so try this. So that's the end of that module. About now, that's a final topic, but what I left is a permutation group. So we will discuss permutation groups. in next lecture. So very important type of groups, and that we cannot miss it. Okay, so we'll see what is permutation group.